Hello everyone and welcome to our presentation. My name is Kamil Raczycki and first of all I would like to thank everyone for joining this virtual workshop today. Let me begin by introducing myself. I am a Master of Science student of Data Science at Wrocław University of Science and Technology in Poland. PhD Dr. Piotr Szymański was the supervisor of my thesis as well as of further research which resulted in the paper presented today. Our research is named Transfer Learning Approach to Bicycle Sharing Systems, Stations, Location, Planning using OpenStreetMap data. Our talk is divided into 8 parts presented on this slide. In the next 20 minutes, we will try to introduce you to the topic and results of our research and answer the following questions. What is our research about? Why did we decide to undertake such research? What data did we use for the analysis? What conclusions did we draw from the research? The COVID-19 pandemic caused a major shift in mobility patterns. Citizens, fearing the possibility of contagion on public transport, have started to use individual means of transport, such as bicycles. This phenomenon forced cities to take quick infrastructural decisions to ensure a better safety of new bike traveler. Due to a rise of bicycle demand, accessibility to bicycles became limited. Many cities benefited from existing bicycle sharing systems, which facilitated the new COVID mobility trends. Cities without any existing bicycle sharing systems were facing problems in a resilient response, as deploying a new system quickly was not possible due to the complexity and cost of the layout design process. Many smaller cities and towns, especially in developing areas, find it difficult to finance such projects even in the economically secure times. Our aim was to develop a new method for planning the layout of bicycle sharing stations. In this paper, we address the problem of cost and time in bicycle sharing stations layout design and proposes a new solution to streamline and facilitate the process of such planning by using spatial embedding methods. We hope to provide urban planning offices in cities with a data-driven support to their intuitions by providing a transfer learning-based model for bicycle sharing stations planning. When trying to plan the layout of a bicycle sharing station in a new city, it often happens that the city does not have any useful data, or the data is spread over different institutions or corporations and is private. The region embedding method proposed in this paper is intended to allow machine learning capabilities to be used to a greater extent than currently available methods. It will use publicly available data from OpenStreetMap, thanks to which it will be possible to apply the method in every city which has spatial data entered into this system. The bicycle sharing systems discussed in the context of this study are mainly of the fourth generation, where this generation includes systems connected to the ITS system, provides real-time data, and allows renting using a mobile app. Fifth generation are dockless bicycle systems that can be picked up and returned anywhere in the service area. We found studies on the system implementations in cities such as Madrid, New York, Seoul, Malaga, Wuhan, and Istanbul. All of these implementations used either government data or corporate GPS data or information on the use of the city's existing cycling system. Two works used crowdsourced data. Most of these works focused on optimizing different criteria. Only one paper focused on embedding regions and using public data, such as our research, but the result was a method for optimizing existing station layouts in Japan. None of the papers found were easily transferable to other regions. Our work is based entirely on public data from the OpenStreetMap website and the layout of bike sharing stations from 34 cities in Europe, which can be seen on the map on the slide. These 34 cities are all cities in Europe with a minimum of 100 stations in the system. As you can see, the cities are spread over the continent, so we hope that the collection is diverse enough to show that the model is able to generalize station neighborhoods and decide which regions should have stations. The smallest city in the set is Ostrava, and the largest are Paris and Moscow. This slide shows an example of OpenStreetMap objects from New York. They are represented as dots or polygons if the object in OSM had a shape defined. Below the street grid, you can see the division into microregions in the form of hexagons. This is a division made using the H3 index developed by Uber. The specific index was chosen because there is very little variation in the shape of regions around the world and because each neighbor is at the same distance, thanks to the properties of the hexagon. Turning to a summary of the data collected, in total we collected more than 10,000 stations and almost 3 million objects from OpenStreetMap. We have removed all bike sharing stations defined in OSM from the collection so that they do not disturb the prediction. The studied regions together cover an area of almost 11,000 square kilometers and translate into 3.5 million regions from the H3 index. The basic framework of our method consists of 5 steps. Firstly, the areas are divided into regions. This is done using the Uber H3 discrete global grid system. For each region, the OpenStreetMap objects that reside in that region are assigned. The second step is to embed the objects inside each region into a numerical vector using an embedding function. Region neighborhood can also be taken into account when generating feature vectors. At the end, a city-scoped min-max normalization is applied per column. In parallel, a partitioning is made into regions containing stations and those without stations to build binary labels for learning. The fourth step is to learn the classifier based on the obtained feature vectors and labels in the binary classification task. Finally, using the learned classifier, a prediction is made and the obtained probabilities are converted into a heat map. For embeddings, we use a simple method that counts occurrences of specific categories. It is worth noting that the method presented here can be used for purposes other than station layout planning, and any other element can be used to generate labels. OSM objects are assigned tags. In the official documentation, there are defined categories that group specific tags on which we have based our divisions. Our simple embedding method uses 20 categories: aerial way, airports, buildings, culture and entertainment, education, emergency, finances, healthcare, historic, leisure, roads for bike, roads for cars and pedestrians, shops, sport, sustenance, tourism, transportation, water, and other. As the regions are themselves quite small, we decided that it would be useful to add additional context to the prediction in the form of region's neighborhood. We use consecutive circles of neighbors to generate the target vector and average them per ring. We then average the vector of each ring using a weight equal to the inverse square. On this slide, we present a summary of the flow of the method and the final set of parameters that is used in the final model. Each parameter can be changed. However, we recommend to use the highest possible resolution of the regions for better prediction accuracy. We normalize the collected data for learning and prediction per column and use the data for learning at a ratio of regions with stations to regions without stations equal to 2.5. Turning to the presentation of our results, let me start with our city of Wrocław. The result of our model is a heat map with confidence values of stations in a specific region. In the bottom right corner, you can see a legend with the values, and white points are the stations in the city that were used for learning. Another example of a city used in the learning is Barcelona. As you can see, the model was able to predict the presence of all stations in the city, but it predicts many more regions than just regions with stations. However, we do not consider this a bug because many of these regions have very similar urban significance. So especially at such high resolution, regions next to each other tend to have similar prediction results. Next city in our dataset is Paris. This map is shown at some distance. As most of the stations are near intersections and close to cycle paths, naturally the model concentrates most of the predictions near the street grid. You can also see that the model has learned to avoid water areas, as can be seen in the example of a Thames River flowing through the City of London. The first example of a city without a bike-sharing system, for which we predicted stations in the regions, is Rome. At the bottom, the larger cluster is Roma Ostiense train station. In the center, there are many restaurants and hotels. On the right, the larger clusters are Termini and Tiburtina railway stations. Another example of predictions for a city from outside our dataset is New York. For Beijing, most of predictions are heavily condensed around the road network. In one cluster to the west of the Summer Palace is a shopping center and a metro station. Next example is a single district in Tokyo. Huge cluster on the bottom is a Shinjuku station. And the last example is a single district in Seoul. There are several public transport stations and many shops and colleges to the north of this district. And to summarize, in our study, we were able to obtain an F-score of 0.8 for some cities in the dataset. The model is easy to train on data from one as well as multiple cities simultaneously. Some differences can be seen in the tagging, as well as the urban functions and city structures themselves. The use of normalization helped to improve the results. We investigated three H3 resolutions, 9, 10, and 11, of which we chose the highest to have the most accurate results. Instead of our simple method, other region embedding methods can be substituted and more sets can be plugged in. To smooth the transitions between regions, regression can be used instead of a binary classification and assign different labels to regions depending on the distance to the point. The method and models presented in this work can be used to shorten the response time and quickly provide city authorities with a hexagon-based heat map of how likely the hexagon is to be a good bike station location. Such areas can be further processed manually by thresholding and human evaluation. They can also be clustered agglomeratively with a maximum distance limit set for points inside one cluster. Such clusters can be used as candidate areas that undergo further investigation. Usually, placing a bike stations requires additional checks, such as enough pavement space or property ownership verification, and working with a set of small areas will speed this process greatly. As a result, city planners or authorities and even citizens can be presented with a bike sharing system proposal in a matter of days and not months, strongly improving the ability of delivering a resilient response. And we showed that using only publicly available data, we can return valuable informations. And the framework is transferable between different cities and different tasks. And we thank you for your attention, and we hope that you found the topic and results of our work interesting.